So the modern atomic theory. Atomic theory is that all matter is composed of atoms. And it grew out of observations and laws. The laws that it grew out of were the laws of conservation of mass. We've talked about that one. The law of definite proportions and the law of multiple proportions. The names of those seem to contradict each other, but they actually do not. So, law of conservation of mass, this is from Antoine Lavoisier. In a chemical reaction, matter is neither created nor destroyed. So again, thinking of atoms as Lego bricks. When you build with Lego blocks, you start out with a certain number of blocks, and when you're done, you have the same blocks that you started with. Lego blocks do not disappear into thin air, and they also don't appear out of thin air, right? That makes sense to us. Well, the same thing is true with atoms. So when a chemical reaction occurs, the total mass of the substances before and after is the same. The idea is that the particles just rearrange like you're rearranging Lego bricks. The particles themselves are indestructible. So here we have an illustration of this. We have sodium metal. Sodium is actually a metal, and it is very reactive and soft. You can cut it with a table knife. Here is a flask of chlorine gas. If we take 7.7 grams of sodium and 11.9 grams of chlorine and we put them together, our total mass to start with was 19.6 grams. These are going to react, they're going to combine and form table salt, sodium chloride. The mass of salt that they form will equal the same mass that we started with, 19.6 grams. Because all of the particles that we started with are present in the final product. We are just combining them. Here, all of the purple sodium atoms are all stuck together, and here the green atoms are going around in pairs, and now we've rearranged the Lego blocks. But the mass is the same. That's the idea of conservation of mass. So here's a conceptual connection. When a log completely burns in a campfire, the mass of ash is much less than the mass of the log. What happens to the matter that composed the log? Where did that matter go? A, the matter that composed the log reacts to form gases that are released into the air. B, the matter that composed the log is converted into energy. C, the matter that composed the log is still present in the ashes but has a much lower mass. And the answer is A. Matter does not get transformed into energy in regular chemical reactions like a log burning. That's a nuclear process, a very specialized thing that we're going to ignore until we get to that point in the chapter. The matter is still present but has a much lower mass. You can't lose mass. Law of conservation of mass. So it's got to be A. The matter that was in the log reacts and it forms gases. The gases get released into the air and float away. And that's why the ashes weigh less. It's because we've lost most of what was in the log. Any questions about that? So what about those proportion laws? The law of definite proportions, all samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. And this was formulated in 1797 by Joseph Proust, a French, I edited these slides. I forget what kind of a scientist, but we could say scientist, a French scientist. He was a scientist of some sort.
This is like saying compounds are in fixed ratios.
Yes. So, as an example here, if we took 18 grams of water and we decompose it, we can break it down into oxygen and hydrogen, we would find that we get 16 grams of oxygen and 2 grams of hydrogen. These sorts of numbers are not things you need to remember. They're just as an example. If we look at that ratio, 16 grams of oxygen to 2 grams of hydrogen. That's a ratio of 8 or 8 to 1, right? So by mass, there's 8 times as much oxygen as there is hydrogen in this sample of water. Oh, shit. Oh, I thought there was another slide there. There isn't. If you take another sample of water and decompose it and look at the ratio of those masses, it will be the same. If you take water from the Kings River and purify it and decompose it, it'll be the same ratio, 8 to 1. If you take water from the ocean and purify it and decompose it, water from the Nile River, right, it will always give you the same proportion. The law of definite proportion. A compound has a definite proportion of element masses. So, conceptual question. Mass ratio of nitrogen to hydrogen in ammonia is 4.7 to 1. If a sample of ammonia contains 10 grams of hydrogen, how many grams of nitrogen? Well, this is just math with proportions, right? So the original statement is saying 4.7 grams of nitrogen for every 1 gram of hydrogen. That's the proportion. So in this sample, 10 grams of hydrogen, well, we have 10 grams of hydrogen. Then how many grams of nitrogen do we have? 47, right? Because if we multiplied the bottom by 10, we multiply by the top by 10 in order to keep that ratio the same. Oops. Any questions? So problems like this, and there are a couple on the worksheet that we'll do on Wednesday, problems like this tend to be hard for 1A students because you've already taken Chem 3A, you've done stoichiometry and all of that fancy stuff before, and so you try to apply that sort of thing to a problem like this, and these laws and problems are very, very simple, and so the challenge is just to not overthink. So here's an actual problem. 2 samples of carbon monoxide are decomposed into their constituent elements. 1 sample produces 17.2 grams of oxygen and 12.9 grams of carbon. The other sample produces 10.5 grams of oxygen and 7.88 grams of carbon. Show that these results are consistent with the law of definite proportions. So we read through the problem, and then we pick out the numbers and write those down, and then we figure out what to do next. Okay, so we've got sample 1 here, 17.2 grams of oxygen, 12.9 grams of carbon, and then we've got another sample over here, (10.5 grams of oxygen and 7.88 grams of carbon. So the law of definite proportions. The law of definite proportions says that if I look at the ratio of the mass of oxygen to the mass of carbon for this sample, it will be the same as the ratio for the other sample if they are the same compound. So we could calculate that. And it's always nicer if you take the large number and divide it by the small number. So 17.2 divided by 12.9. The calculator shows 1.33 repeating. Or that would be what, 4/3, right? And over here, 10.5 divided by 7.88. And this is giving me 1.33 by significant figures. That's where I would stop. The next two digits are 2, 4. But that is also essentially 4/3. The ratios are the same. This sample has less oxygen, but it also has less carbon. That sample is smaller, right? Any questions? Then we have the law of multiple proportions. This one applies to two different compounds. So if we have two elements, we'll just call them A and B, and they form two different compounds with each other. The masses of element B that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. And this was published in 1804 by Dalton. So what exactly does that mean? It's a bit confusing. If you take the ratio of element B to element A in these two different compounds, the ratios are not going to be the same because the compounds are different. What this is saying is that if you take the ratio of the ratios, you'll get a small whole number. That's just almost magical. Like, wait, how does that happen? Well, let's look at that. So carbon monoxide and carbon dioxide, two compounds composed of carbon and oxygen. But the ratios of atoms are not the same. In carbon dioxide, there's 1 carbon atom and 2 oxygen atoms. In carbon monoxide, there's 1 carbon atom and 1 oxygen atom. So we could anticipate that the ratio of oxygen to carbon by mass is not going to be the same, right? Because this one has twice as many oxygen atoms. So if we look at that, for carbon dioxide, we'll get 2.67 grams of oxygen combining with 1 gram of carbon, a ratio of 2.67 to 1. And in carbon monoxide, the ratio is 1.33 grams to 1. Right, well, okay. Law of multiple proportions says if we take these two proportions, take the larger one and divide by the smaller one, 2.67 divided by 1.33, we get a small whole number, 2. Why does that happen? Well, it's because of the numbers of particles. This molecule has twice as many oxygen atoms as this one does. There is nothing in between. You can't have 1 carbon atom and 1.5 oxygen atoms. It's just not possible. The ratios have to be small whole numbers. Another problem. Hydrogen and oxygen form both water and hydrogen peroxide. The decomposition of a sample of water forms 0.125 grams of hydrogen to every 1 gram of oxygen. Decomposition of a sample of hydrogen peroxide forms 0.0625 grams of hydrogen to every 1 gram of oxygen. Show that these results are consistent with the law of multiple proportions. Okay, so we read all the words. There's so many words. And then we'll pull the numbers out. So here we've got water, and that's giving us 0.125 grams of hydrogen for every 1 gram of oxygen. And then we've got hydrogen peroxide. And this one has a mass ratio of 0.0625 grams of hydrogen for every 1 gram of oxygen. So we've got ratios there. We can express them just as a number. So this would be 0.125, and this would be 0.0625. To demonstrate the law of multiple proportions, we need to see, is the ratio of these two numbers a whole number? And it is. You always want to take the larger number and divide by the smaller if you want to get a whole number. So 0.125 divided by 0.0625. Two. The reason for that is water has 1 oxygen to 2 hydrogens. Whoops. Hydrogen peroxide has 2 oxygens for every 2 hydrogens. There are twice as many oxygens here, so the ratio of hydrogen to oxygen is twice as large for the water as it is for the hydrogen peroxide. Any questions? So, John Dalton came up with the atomic theory, published in 1808, and this is a very important theory. So, this is one name here, Dalton, that it would be a good idea to remember. You can absolutely pass the class without having a clue who John Dalton is, but what's really important is to understand these ideas. And I'm not going to ask you to list them all out just out of nowhere. But you need to understand what they are. You need to be able to recognize them, say, in a multiple choice question or something like that. So the first idea is that each element is composed of tiny indestructible particles called atoms. All atoms of a given element have the same mass and other properties that distinguish them from atoms of other elements. Atoms combine in simple whole number ratios to form compounds. Atoms of one element cannot change into atoms of another element. In a chemical reaction, we only change the way the atoms are bound together. The atoms themselves do not change. Today, the evidence for the existence of atoms is overwhelming, but in 1808 it was not. So this theory was a big deal. Is every statement in this theory correct? No. It appeared to be correct in 1808, but we now know that 2 of these statements are not quite correct. That doesn't mean we throw out the whole theory. It means that we modify the theory. So we'll talk about which ones those are as we go along.